So we're going to be looking at exponential functions. Now, exponential functions are basically functions where x is in the exponent. So here is the general form of the equation for an exponential function, a to the power of x. Now, that value of a can differ, but a needs to be a positive number, and it just can't be 1 because really that would make it pretty boring. So any other positive number besides 1. Now, as far as the normal graph goes, here is the general shape of the graph. But depending on certain situations, what that value of a is, to be precise, the graph may change. So this is just a general parent function for exponential growth, which we'll look at further in the video. But there's also a decay model that looks more like that. And depending on what the value of a is, depends on like starting order pairs as far as key points in the graph. But the main key point that doesn't change, whether it's growth or decay, is the point 0, 1, as well as the asymptote. So, parent function. The characteristics of parent function includes the horizontal asymptote at y equals 0. That's the orange dotted line. Domain of exponential functions are all real numbers in general. Range is typically y greater than 0 for the parent function. Now, given transformations and other things, combining it with other functions, that may change. But for the parent function, the domain is y greater than 0, whether it is a growth or decay model. Exponential functions have no x-intercepts. Again, we're talking about the parent function right now, the very basic exponential function. Y-intercept is at 0, 1 as far as the basic parent function is concerned. Now, end behavior is a little bit funky. On one side, as y will approach positive infinity, and on the other, y approaches 0. This is dependent on whether it's a growth or decay model. So this image here is a growth model because it goes up from left to right. And on the left side, as x approaches negative infinity, y approaches 0. While on the right side, as x approaches positive infinity, y approaches positive infinity as well. For the decay model, it will be kind of flipped around, where we would flip the y approaches 0, or y approaches infinity, and y approaches 0. So in this example, we are going to be writing the equation for g of x when the function f of x equals 2 to the power of x is dilated vertically by a factor of 4 and translated left 3 and down 2. Now, a lot of times when we write equations using transformations, we might have something sitting there. We might have something inside with x, and we might have something outside. That's typically the format when writing equations with transformations. It can be a little bit weird with exponential functions, but here is the basic function, 2 to the power of x. So when we are writing the equation for this g of x, making sure I'm using the correct letter here, g of x equals, we might be multiplying something in front, times our 2 to the power of x, possibly plus or minus something, and then possibly something off to the side. The stuff inside the exponent with x, it affects the x values in the opposite way, just as like it has done in the past, and the stuff outside will affect the y values, just like we've seen in the past. This 2 to the power is similar to our squared and quadratic functions, which just tells us the basic characteristics of the graph, what type of function it is. This is an exponential function with a growth factor of 2. Now that key stuff is taken care of, let's go ahead and try to write this equation. So we're dilated vertically by a factor of 4. That means we're going to be multiplying our y values by 4. And we're translating left 3. So if we're translating left 3, that means we're taking x values and subtracting 3. And we're also translated down by 2. So in addition to multiplying by 4, we're going to subtract 2 as well. Now if we just set this up in the equation, starting with the y stuff, dilation, multiplying by 4. So we're going to multiply our 2 by 4. Remember, we can't actually multiply them because of the exponent, so we'll just sit out in front. We are also subtracting 2 from the y values, so since it affects y, the operation will stay the same and it will be outside. So we'll tag on a -2. And we are subtracting 3 from the x, so inside x opposite means we're going to do x plus 3. Now if I clean this up a little bit without the highlightations, we'll have g of x equals 4 times 2 to the power of x plus 3 minus 2. You could also write it with parentheses instead of the multiplication dot, which you need to do for fractions, but not for whole numbers. And there we have it. Okay, in this example, we're going to be graphing the function f of x equals -3 times 2 to the power of the sum of x and 1. And we're also going to be describing the transformations. So I'm going to go ahead and set up my initial transformation rules. Remember that this number inside the parentheses that has the exponent is not a transformation. It instead just tells us the basic characteristics of this basic exponential function, 2 to the power of x. So our transformation rules here, outside y same, we have a times -3 on the outside, so we're going to do y times -3, and inside x opposite will be x minus 1. So those are our transformational rules. Now as far as to graph this, I'm going to continue to use just reference points to help myself out with this, just like I've done throughout most of the lessons. But this is an exponential function, 2 to the power of x. You can use some other notes from an earlier part of this video, which tells us the general points are -1, 1 over a, 0, 1, and 1, a, as well as the asymptote y equals 0, which is always the same. The a in these points just refers to the base, because normally an exponential function might be written as a to the power of x. In our case, it's 2 to the power of x, so it's -1, 1 over a, or 1/2. 1 over a, 1 over x just basically means the reciprocal of that value. So reciprocal of 2 is 1/2. 0, 1, 1, a, which is 2, and then y equals 0. Now, usually I just use 2 reference points whenever I graph this. I usually don't use the fraction one. You can always use the fraction one if you need more detail, but usually the 2 points and the asymptote are good enough for most purposes in Algebra 2. Now that I have some reference points to help me plot and draw the graph, I'm just going to start off by subtracting 1 from my x values. So we're taking our x values and subtracting 1. 0 minus 1 is -1. 1 minus 1 is 0. And the asymptote is an x or a y asymptote, so it's not affected here. Our rule for y is to multiply by -3, so 1 times -3 is -3. 2 times -3 is -6. And then 0 times -3 is still 0, so our y asymptote actually didn't change. Now we'll go ahead and start graphing stuff. I like to start by getting the asymptote on first. So it's a horizontal line where y is 0, so right along the x-axis still. This is where it normally is if there's no translations involved. We have the point 0, -6. For some reason I'm going upside down, starting from the bottom. So 0, -6, and -1, -3. -1, -3. So now to draw the shape in, what I usually do is I look for which of the two reference points is closer to the x-axis, or not the x-axis, the asymptote. In this case, this one is the closer one. So I will start on the left side of my graph. I will hug the asymptote, curve through the points, and off the graph. So when I draw it in, I hug the asymptote, and I accidentally draw too close. Whenever I get too close, it cancels the writing. But hug the asymptote, curve through the points, and off the graph. So this one jumps off pretty drastically there before it even gets halfway through. Remember that it will not cross the asymptote. It just hugs along it and then curves through the points. And that is the graph of this function. Now, as far as describing the transformation part, just as I've done in the past, describing the transformations involves the operation. So multiplication creates a dilation. So dilation, so long as that number is not 1 or -1, this is -3, so it's going to create dilation vertically. Since we're multiplying y values by a factor of 3, the negative actually creates a different type of transformation. The negative portion creates a reflection across, in this case, the x-axis. Since it's affecting y values, it's actually going to reflect it across the x-axis. And lastly, we have a translation from the addition and subtraction. So we're translating, since we're subtracting 1 from x, it's going to be left 1 unit. And these are the transformations for this function, from its parent function 2 to the power of x. So in this example, we're going to be graphing the equation f of x equals 1/2 to the power of x, and then not inside the exponent. Make sure it's clearly noted that this 2 is not inside the exponent, but we will subtract 2 from 1/2 to the power of x. Then we're going to state domain, range, and end behavior. To do this, first of all, let's go ahead and identify our transformations. So 1/2 this time is our base. That's important to know. 1/2 has the exponent, which means 1/2 is not a transformation that's happening here. With that being said, the only other number we have is the -2, which means we only have one transformation. We're taking our y values and subtracting 2. That -2 is not inside the exponent, not with x. Therefore, since it's not inside the exponent, it is considered to be the outside stuff, which affects our y values. And in the same way, as far as our starting order pairs, this time the parent function, the specific parent function, is 1/2 to the power of x, which means if we look at our generic points for reference points, -1, 1 over a, 0, 1, and 1, a. Well, 1 over a again means reciprocal. So our generic points will tell me that it's -1, the reciprocal of 1/2, which is 2. Reciprocal. If it wasn't obvious, I can't spell, so don't trust that spelling because it's completely wrong. For the second point, it's always 0, 1. And the third point, 1, a, so 1, 1/2. Which that's not a 1/2. There we go. And then the asymptote that we'll always use, y equals 0. And like I said with the last example, or possibly previous examples, we're not going to use the fraction. You can if you want to. It's just a little bit harder to graph, and we don't really need that third point to help us get the shape correct. With that, let's apply our transformations. We only have one transformation going on here, and that's our y values -2. So our x is staying the same, -1, 0, and doesn't affect the y asymptote. And we're subtracting 2 from the y values, so 2 minus 2 is 0. 1 minus 2 is negative 1, and 0 minus 2 is negative 2. With this, let's go ahead and plot things. So we have our asymptote y equals negative 2, horizontal line where the y values are all negative 2. There we go. We got the point 0, negative 1 right there, and the point negative 1, 0. I think I'll put them in different colors just to emphasize them since they are easily mixed up. 0, negative 1 is this one, top of the fact that I'm doing them in reverse order here today. And negative 1, 0 is this point here. When I go to graph this function in, I usually start on the side that is closer to the asymptote. So the red point is closer to the asymptote, distance of 1 versus distance of 2. So I'm going to start on the right side over here, which means I'm going to start by hugging that asymptote, and then I'll curve up through the points and just off into space. There we go. That is more or less the graph of this exponential function. I believe this is probably increasing a little bit more dramatically than what I have it here. But yeah. Now let's go ahead and take care of the key features for this function, or some of them at least. Whereas for domain, range, and behavior. So domain for an exponential function is all real numbers. There are weird exceptions sometimes with restricted values for different applications, but in general, the domain of exponential functions is always all real numbers. The range is usually a restricted value, or always a restricted value. So normally, the parent function has a range of y greater than 0, not equal to because of the asymptote, and because of our transformation of y minus 2, this is going to change to be y greater than negative 2, subtracting 2 from our y value. Since we don't multiply or divide by negative, our inequality sign will stay the same. And even if you do it the old-fashioned way on our graph, lower bound we stop at negative 2, upper bound we hit it and run off, we can still get the same result no matter how you go about approaching doing the range. For end behavior here, remember for end behavior we have a left side and a right side. So left side, well, if we look at the graph, start in the middle somewhere and go to the left side goes upwards, while the right side, if we start in the middle and go to the right side, we level off at the y value. That y value corresponds to the asymptote. We will never actually cross that asymptote. So while we do appear to be going down, since there is an asymptote, we stop at that asymptote. We never actually reach it, but we do approach it. So I like to write it out in words as a level, if I could only spell that, level off, y equal to negative 2. We don't actually reach negative 2, but that's where we're trying to level off at. Now mathematically, left side is described as x approaches negative infinity, because there's negative x values on the left, and up is described as y approaches positive infinity, because positive y values are up. For right, it's x approaches positive infinity, because positive x values are on the right. And then the leveling off, y approaches, well, we are approaching the y value of negative 2 as we get closer and closer to the asymptote. So there is the two end behaviors for this. Of course, our range and our domain. Okay, now you can see that this set of definitions and stuff specifically address exponential growth and decay. And oftentimes when you talk about growth and decay models, you'll change the formula up a bit. So you can see in one of the earlier examples and stuff, I was using a to the power of x. However, here you can see them using b to the power x, where b is representing the same thing a was on the previous one. For exponential functions, depending on where you look, you could see all types of different equations, just because depending on the use for those equations depends on how they're kind of written. But either way, a growth situation is when that value with the exponent is a number greater than 1, while a decay situation is when that number is between 0 and 1. You can see that the graphs have basically the same shape, just kind of reflected across the x-axis. Yeah. So, very similar characteristics. They are actually all the same characteristics. However, this has a big issue, which happens when you kind of take stuff out of resources. So right here, this issue is, let's try to fix it here. It's not equal to, range does not include that asymptote, so I need to cover that up there. You saw nothing. So yeah, range does not include that asymptote, or where the asymptote is, so cannot have a value there. And based on how these functions are written with the exponential growth and decay, the y-intercepts are at 0, comma a, because they have a multiple of a along with it. End behavior, as mentioned in one of the earlier examples, one side will be going up and the other side levels off, and it just reverses with decay. General format for a growth model might be 1 plus r, where the growth factor is 1 plus r, the decay factor is 1 minus r, but that's not to say how much it's growing by or how much it's actually losing. So in this example, we have a population of town that is about 5,300 in the year 2015. The population is predicted to grow at a rate of 2.5% for the next 5 years. We're going to be writing an equation for the situation. Normally, whenever you're writing the equation for the situation, you'll use x or t, either way, to represent time. For time, or usually years, since the starting information. So in our case, years since 2015. And I think I'll just go with x, just because I feel like using x this time. I'll probably use t a different time. So x years since 2015. So to write an equation for the situation, if we're taking in exponential growth or decay model, we are going to have y equals, or f of x equals, a starting amount, times 1 plus or minus r, depending on the situation, to the power of x. Our situation is a grow model, so growth rate, which means we're going to be looking at 1 plus r to the power of x. Now r here is going to be the rate as a decimal, while this is the entire growth factor. Usually a represents the starting amount, and then x represents our time in years. I'm going to highlight that because it kind of blends in since I used the same color. Okay, so to actually write the equation to model this situation, let's go ahead and fill some stuff in. Of course, we'll still have our y, which is representing our population. We have our a starting amount, our 5,300, times our 1 plus our rate as a decimal, so it's 2.5%, Remember, when you use percents, either divide it by 100 or move the decimal place over 2 spaces. So it's 1 plus 0.025 to the power of x. In other words, we have y equals 5,300 times 1.025 to the power of x as our equation. You may also see people write it as y equals 5.3 times 1.025 to the power of x, and they might just label y is population in thousands. And that's just an alternative way of doing it. Since my number isn't that big, thousands isn't too bad, I think I'll just stick with this version. Now part B. Part B is asking us to actually predict what the population would be in the year 2027. So for the year 2027, that would be how many years after 2015? Well, that would be, it looks like 12 years after 2015. So it would be when x is 12 for part B. If we go through and actually try to use our equation to find this, it's a simple matter of just plugging it in. Y gives us the population, x being time. So y equals 5,300 times 1.025 to the power of 12. You can either go through and work that out by hand, which might be a little bit annoying to do with this, or you can just type it into most calculators. So 5,300 times 1.025 to the power of 12, which gives us a population of about 7,127, since it's population, I'll round to the nearest whole, so about 7,128 people. And there we have it. Okay, so in this example, we have a computer that's purchased for $600. The function y equals 600 times 0.7 to the power of x can be used to model the value of the car, which I forgot to change that word, computer, x years after it was purchased. Does the function represent exponential growth or decay? And what is the rate of growth/decay? So if we look at this, here is the equation that part of the equation we're going to focus on. The y equals 600 times 0.7 to the power of x. This right here is the factor. Now you can see that this number is between 0 to 1. Since it's between 0 and 1, this represents a decay. So the decay factor is 0.7%, or 0.7. Now, let's actually take a closer look at it and look at the decay rate. The decay factor and the decay rate aren't the same thing. The decay factor is how much is left, but the decay rate is how much is lost. So, slight difference in words there. So, left after a year. And if we break this down, normally, this is a result of taking 1 minus our decay rate to get the decay factor, which is currently 0.7%. Well, some simple math, you can easily figure out that it's 0.3. If you have a hard time with that, you can just subtract 1 to get negative r equals negative 0.3, and then divide by negative 1, And you would see that the decay rate is 0.3, which as a percent is 30%. So decay rate is 30%, which is how much is lost each year. So this computer loses 30% of its value each year. So we kind of answered both pretty quickly there. Just summarizing, it is a decay because of the value between 0 and 1. Growth is bigger than 1. And then the factor, the decay rate is not actually what you see, but it is the result of taking away what you see from 1. Okay, in this last example, we have a museum which is purchasing a painting and a sculpture during the same year. Their changing values are modeled as shown. We're going to find the average change for each value or each piece of artwork over the 5-year period, and then determine which artwork is increasing more quickly over that 5-year period. So since we're looking for just an average change between when they're bought and the end of this 5 years, we're going to be using average rate of change. Remember, average rate of change is just the slope. So we are basically looking at slope y2 minus y1 over x2 minus x1, as well as many other versions of the formula that you could use. So I'm going to start with one from the graph because the graph is usually easiest to do. We have two ordered pairs very nicely given to us. So the second y value, so I'll just call these ones x1 and y1, x2 and y2. So I'll take my second y value, 64.4, minus my first y value of 40, divided by my second x value, minus my first x value. If I do the subtractions, 64.4 minus 40 is 24.4 divided by 5. And I don't know what that is. 24.4 divided by 5 is about, or exactly actually, I don't need to say about, 4.88. Now let's go ahead and compare with the one that we're given an equation for the sculpture over here. Now, the sculpture doesn't actually give us any values as far as points to use. However, we know that year 0 will be the original cost, and year 5 would be 5 years later, which is what we're trying to compare. So we know that the x value is 0, and x value is 5. So if we plug 0 into this equation, we should get 50, because this is an exponential growth model. Anything to the power of 0 is 1, but let's just do it, because I know some people won't believe me. I have students all the time not believe me, be like, what? So I'm just going to type it in and show it. So we have 2 to the power of 0, and as you can see, what happens is the 1.025 to the power of 0 becomes 1, and the 1 times 50 is still 50. So the first point we have is 0, 50. And at year 5, so let's go ahead and just change that to a 5, we have about 71.78. I think I'll keep 2 decimal places. That's probably enough to show what we need. So looking at this, let's go ahead and label x1, y1. x2, y2. And we'll go ahead and set it up. Our second y value, 71.78, minus our first y value of 50, over the second x value of 5, minus our first x value of 0, gives us 21.78 over the 5-year period. You can already see that the other one is a bigger number on top with the same number on the bottom, so we should expect a smaller number than 4.88. So 21.78 divided by 5. And as expected, it comes out to be 4.356. So what these two slopes are saying right now is that each year, the value in thousands of dollars goes up. So this is value in thousands of dollars. So about $4,000 per year is the value that this sculpture is increasing by. And same thing goes for the painting. However, the painting is increasing, has a greater growth rate over this 5-year period. So the painting has a bigger growth rate. And that's our conclusion.